Hello, welcome to this Copernicus Marine Service training session on the Baltic Sea. My name is Mathilde. I'm a scientific engineer at NOVELTIS in France, and I will be your trainer for this sea ice practical session. We will work in the Jupyter Notebook environment, and the first thing you have to know is how to validate a cell. To do so, you can click on this button, run the selected cells and advance, or you can use the shortcut Shift plus Enter. And if for any reason during the training the kernel is not working anymore, you can click on this button, Restart the kernel, and then in the top menu, Run all above selected cell. That will validate all the previous cells and will enable you to continue the training. There are 6 different notebooks for this training, but I will go into details only for 4 of them because the 5th and the 6th one are very similar, and you will be able to do the exercises by yourself. Each notebook has the same architecture with an introduction and a description of the data that are used, and then the exercises. We will look at the different CMEMS products that give access to the sea ice concentration or the sea ice thickness information in the Baltic Sea. And this is very important because, as you know, the Baltic Sea is a very busy sea with a lot of traffic of vessels, and also difficult sea ice conditions during winter. So we are going to look at the winter sea ice conditions during the 2017 and 2018 season. So for this first notebook, we will look at the CMEMS physical model products, which provide sea ice information. There are 2 different model products, to study the sea ice coverage in the Baltic Sea: the analysis forecast products and the reanalysis products. The analysis forecast products are provided at different time frames, so hourly, daily mean and monthly mean products, and they all contain the same parameters: the temperature, the salinity, the sea level anomaly, the currents, the sea ice concentration, and the sea ice thickness. The reanalysis products are organized differently, and only the hourly surface products provide the sea ice concentration and the sea ice thickness. So you won't find the sea ice information in the daily mean and in the monthly mean 3D products from the reanalysis. So in this exercise, we use the monthly analysis forecast products. And if you want more information about these different products, you can simply click on these links and you will access directly to the CMEMS webpage for these products, where you will be able to find the user manual, the quality reports, and the links to download the data. All the CMEMS products are stored in an NetCDF file, which is a very common format to store scientific data. And these files contain a lot of information about the data, the dimensions, typically the time, the latitude, the longitude, the depth, several variables which depend on one or more of these dimensions, and each variable comes with its own attributes, such as its unit, its name, the field value, the scale factor, the mean and max values, for example. And finally, we have global attributes that give general information about the product. But first, because we use Python, we need to load libraries before looking at the data. So we are going to call a number of libraries that will enable us to handle the data and to load the netcdf files and to plot the data. So to import these libraries, I will validate this cell. And as I said previously, you can do it either by clicking on this button here or by using the shortcut Shift plus Enter. And you see that it has been validated because now there is a number here. So a bit more about the physical model product that we are going to use, the analysis monthly mean product. It's a regional product for the Baltic Sea. It's a monthly mean product, and it's a 2 kilometer horizontal resolution with 25 depth levels. It is available from 2016 to today, and we downloaded a subset of this dataset for the period from September 2017 to May 2018 to cover the whole winter season. All the data have already been downloaded for this training, and you will find them in this folder here, where there are different datasets, model data and observations data. So first, we need to tell the notebook where the data is stored. So we do it in this cell by defining a path and the file name. So I will validate this cell. And then we use the OpenDataset function from the Xarray library to open and browse the file content. So you can see now the different information inside the file. So the coordinates, longitude, time and latitude, the dimensions, so the number of latitudes and longitudes that forms the grid of the model, and the number of time frames. And then we have two data variables, the cconc and csic. So if we expand here, we can see that the first variable is the sea ice cover, and the second one is the sea ice thickness. So the first one is given without any unit, between 0 and 1, and the second one is given in meters. If I hide this information, you can also access here the total number of values inside the variable and the type with which it is written inside the file. And finally, you can access the global attributes of the file, that is to say, all the information about who produced the data and the spatial extension of the grid, information about the depth here, and the grid resolution, and many other information. And if we want to store all this information into a variable, we do it like this, by defining a variable fin and calling the OpenDataset function again. And then we can show some information from the dataset fin using the info function. So we see here all the dimensions, coordinates, data variable, and so on that are available inside the product. Of course, there was a mention to the depth before here, but for sure, there is no dependency on the depth for the sea ice concentration and the sea ice thickness. So the dataset is only 3D with time, latitude and longitude. Then we can access the global attribute values by calling this function here, and with the exact name of this global attribute, for example for the easternmost longitude of the spatial domain. So here if I validate, I see that it's 30.3 degrees east, and that's exactly the value that is written here. Then we can access information about the variables inside the dataset using data_vars function. So we see there are two variables with these coordinates. The coordinates, so again, longitude, time and latitude, and their values here. The dimensions, so again we have 9 time frames for the 9 months, and this is the grid for the latitude and the longitude. And if you want to access the values of a variable inside the dataset, we can call it, we can call this the values function. So we need to say that it's in the fin dataset that we want the time variable, for example, and the values of this time variable. And here we display all the time frames. So we see that we have one time frame per month. Of course, we can store this information into a variable itself, a new variable, so var time, for example, here, and then we can print what is inside var time using the print function. And again, we see all the time frames. Another way to look at the product is to use the ncdump Linux command. You can call Linux command from a Jupyter notebook simply by inserting an exclamation point before your command here. So we call the ncdump function with the file name here, and we will print the header of the file. And you see all the same information, so the dimensions and all the variables with their attributes and the global attributes of the file. An interesting point here is for the time. You see that originally in the file, the time is stored as days since the 1st of January 1900, whereas, well, which makes a big number of days, whereas Python automatically translates this information of number of days into a human readable date, which is very convenient. So now that we know how to look at the data and how they are built, we can draw our first maps. So we are going to look at the sea ice conditions during the winter 2017-2018. And first, we need to select the file that we will open and the variables that we want to plot. To do that, you have two options. Either you plot the sea ice concentration, or the sea ice thickness. So there are two different cells here, and you have to validate only one of them to define the variable that you want to plot. So we are going to start with the sea ice concentration. So we have the path and the name of the file we want to open, the name of the variable we want to load, a name for the plots, a unit, and because we want to plot it as percentage and not as a value between 0 and 1, and then min and max values for the color bar. And we have exactly the same thing for the sea ice thickness if you want to do it later on. Then I open the dataset and I store it into a variable here, and then I store the time, the longitude and the latitude values in specific variables. And finally we store our variable into, so here the CIS concentration, into a specific variable, and we multiply it by 100 to have percentage. Okay, so we have here our new array or new variable that is displayed, and you can see that there is only one variable, which is the CIS concentration, and again the coordinates, and that's it. Then we will generate the plots. So first we create a folder where we'll save the plots linked with this specific variable. So we're going to create this folder in the out folder that you can see here, which is empty for the moment. So I validate the cell, and now you can see that the folder has been created, and this function doesn't create again a folder if it already exists. It tests if it exists. Then we can map the data. So first we're going to map the CIS concentration at two different dates, for December 2017 and in March 2018. So very different conditions. To do so, we need to select the date inside the product, because we want to plot only one date. So here is the date we want to, the two dates we want to extract, and here with the cell function we find the date and the time index that corresponds to the date we want to plot, using the nearest method. So we do it for the first date and we do it for the second one. And here you have the variable selected at the first date. So it doesn't depend on the time now, because we just have one dimension for the time, because it's one date. You can see here the time is now the 16th of December 2017, so that's the first date. And for the second data set, we have the correct date here, 16th of March 2018. A little point on the how you can handle the dates with Python here. You see that here it prints all the information about the date, so the year, the month, the day, the hour, the minutes and the seconds. But you can reduce this information. For example, if you want to display only the date up to the day, and you can do it with the asType function here. So you have here an example where we limit the display to the day with this big D, and here you can see it, the original date and the limited one to the day information. Okay, so now we are going to plot the data. To do it, I propose to show two different methods that's very simple. The first one, we will plot one figure per date. So we use the figure function, and then we will use the base map, mesh grid, map and picolor mesh functions to plot the map. So first we define a plot window, the region where we want to plot the data. We create a figure for the first date, and then we create a map. We put a lot of information on it for the geographical information. Then we use the mesh grid to create a grid from the longitude and the latitude, and we put the variable at the first date with the pcolor mesh function. Then we add some information with title, X label, and Y label, and we save the file. And we do exactly the same thing for the second date. So we create a new figure and we do all the same, except that we use var_date2 this time, and we save this file in this plot in another file. So I validate the cell here, and here are the two figures. So you can see in December very low sea ice concentration. There is only a bit of ice in the northernmost part of the Bosnian Bay, and a bit in the Gulf of Finland. Whereas in March the situation is completely different, with a much larger sea ice cover. Okay, another way to plot the same information is to use the subplot function. So this time we're going to have one figure, but two subplots, one per date. And to do so, we define this figure here and two different axes. And we will put one date on each axis. So I won't go through all the details. You can look at it if you want. And I save only one file this time, because we put all the two dates on the same figure. And here you have the two plots. So it can be easier to look at if you have two plots on the same figure. Okay, so the conclusions are the same, of course. So we can plot the same for the sea ice thickness. If I go back to the selection here of the information, so this time I validate the sea ice thickness cell. Okay, I open again the dataset. I store time longitude. I store the new variable, and I multiply also it by 100 because it's given in meters, and I feel it's easier to read it in centimeters. Then I create, so you see that we have this sea thick variable here now. I create a new folder to save the plots for the sea ice thickness this time. And then I prepare the data to be plotted, and this we already did. And I go directly to the option 2, where I will plot the two subplots on the same figure. Okay, so this time we have the sea ice thickness here, and again we see that in March we have a much thicker ice than in December. Okay, so now we are going to plot the data for all the dates for the winter season in 2017-2018. So we'll plot the variable for the 9 months of data, and again we will use a subplot function, and we are going to loop on the time values. So we are going to plot the sea ice thickness. I validate the cell, and you can see here that it is running because there is a little star close to the cell. Okay, so now we have all the plots and for the sea ice thickness, and we can clearly see the evolution over the time with a maximum in the month of March. Of course, you can do exactly the same plots again with the sea ice concentration. So that's it for this first tutorial, and let's jump to the second one.